Okay, can we start? Okay, let's start with continuous fraction. So what is continuous fraction? It's simple. It's just a way of writing the rational number, or it could be the approximation of the irrational number. But I'll give you an example of continuous fraction. So from something like this is continuous fraction. So you have lots of 1 over something, 1 over natural number going on. So you have to go backward to compute what the rational number is. So we have 1 plus 1 over 7 over 3. So it's 1 plus 3 over 7. So it's 10 over 7. So you can rewrite or express this continuous fraction in a different way. So one way you can express is what you can found in a old text. So it's 1 over 2 plus 1 over 3, something like this. So instead of writing lots of lines to represent actual fractions, you can abbreviate those lines into single line. Or sometimes just people write it the sequence, just 1, 2, and 3 here. So 1, 2, 3 goes here to represent a continuous fraction. Okay, so why we're considering continuous fraction? There are many reasons in number theory, but in our situation, we want to find the rational number satisfying these conditions. So we have 2 to the n over y, r over j, 2n plus 1. So this is what we know. This is what we don't know. But what we want is we want to find rational number j over r, and we're particularly interested in finding r satisfying this inequality. So let's take more inequalities here. So since r is considered to be less than 2n over 2, because what's the point having a period not running at least twice in the entire sequence, because that might be not considered as a period. So we have to assume that our sequence, 2 to the n number of sequence, are long enough so that it contains at least twice of iteration going on of this periodic sequence. So therefore, you can say this is time less than 1 over 2 times r squared. So this is what we want. So we can just say this is some rational number x, and this is some rational number p q over p here. We want to approximate x by rational number q over p, where this p as now it's a period, So P is of course bigger than 1, but it's less than 2n minus n over 2. So that's where we need continued fraction. So theorem here. So yeah, I'll state the theorem and then try to think about why the theorem helped us to get this P to Q over P. The theorem says if x over Q over P is less than 1p squared, then so let's see. So then x is I should introduce some terminology before I state the theorem. Okay, so let's leave this theorem a little bit behind after we explain the terminology here. So and then let me talk a little bit more about continuous fraction. So let's say this is our continuous fraction, a0, a1, up to an. Okay, so as I said, this is continuous fraction a1 plus, a0 plus, a1 plus, a2 plus, till we have 1 over an. And let's call this Pn, Qn. So if we progress our series, a sequence an further, we get another, every time we get another continued fraction, and therefore we get another rational number. So we can make a sequence of rational number by adding more numbers to the sequence. So and also if we get more and more numbers in the sequence, then we get more and more accurate value that we converge. So let's say each of this Qn over Pn given as continuous fraction converges to some number. This x could be rational number or irrational number, it doesn't matter in principle. Then each of these number is called convergent of x. Okay. So that's what I wanted to introduce before I state the theorem. So then, if that is happening, then this P over Q is the convergent of x. So, yeah. So if this inequality is true, then what we are trying to look for, satisfying this inequality as Q over P type rational number, appears as a convergent of the number x. So there should be a continued fraction, which is the rational number that converges to x. And if we lay out as a finite sequence, so if x is rational number, it will end at a certain index, right? Because every rational number can be represented as a continuous fraction with the finite sequence. So this end, the index, will terminate at a certain point. However, you can find one of the convergent of the x as a continued fraction satisfy this inequality and no more. So you always find such Q over P as a convergent of x. So let me show you how you can actually apply this to find the period. So and then let's go back to the continued fraction part. So here, I'll show you. I want to look up the numbers that I want to make as an example. Here, yes, so it's big number. Let's see. Okay, so maybe we can use this one. 11490 214. How big is 214? It's too big. Okay. So maybe okay, so let's keep this one. 11490. How big is 2 to the 14th power? I think I should use calculator. So anyway, so this is our x here, which is 2 to the n y over 2 to the n. So therefore, you can assume that n is 14 and y is 11490. So remember that our quantum circuit is designed with the quantum Fourier transform that can measure y on the input register. The output register doesn't matter. The input register, we measure 11490. And then we use the 14 input register to compute this. And this is our result. So let's try to find out its continued fraction. So how much is 2 to the 14th power? So let me compute. Let me go to here. Let's see. Four nine zero two 14. Oh, really? Okay. So it's 16 3 8 4 11490. Okay. So first, you have 0, and you have 16 3 8 4 11490. So it's 0 plus 1 plus 4984 11490. Okay, so you have to do I mean, you don't have to do it by hand, but I'll do it for few of them. So just so that you can get the idea how continuous fraction look like. So now you take the reciprocal of 4894 with 11490. You get 11490 4894. So this is 0 plus, so I'm going to write this way. So it's 1 plus 1 over, how many? So 2 plus, and then you get 1 over, so now, so let's write it this way. So 8, 8, 7, 9, right? So you get what? 9788 over 2 0 6 1, right? No, sorry. So 9 8, so that's 4894. So basically you can write it as a the form of rational number, but I just abbreviated it into one line. So anyway, you can keep doing it. Then what you can find is a sequence of numbers 1, 0, 1, 2, and so on. So let me go back to the slide. It's already computed here. So it keep going on. So 2, 2, 1, 7, 35. Going on. Now, this is x. This is what we already know. This is x. We want to find another rational number that has a error less than 1 over 2 to the p squared. So theorem says we can only find that rational number in the convergent of that x. So we should search by increasing the length of sequence in the continued fraction, which one of those are satisfying, and which one of those satisfies our condition. So first, let's take 0, 1. So check which one satisfies the condition. So what is 1, 0? It's 0 plus 1. So it's just 1. Okay, so that's not what we want, because if we have this number, so the problem is the problem is we don't know what p is. We simply don't know what p is. So basically we don't know what the radius at the period r here. So we cannot get what this actual the limit bound upper bound of our error term is. But what we know is this r cannot exceed the half of our denominator of x, so 2 to the n. So at least the 1 here. Now, if I took this as my p over q over p here, so what I'm having q and p is just 1. So then I get 11490 over, what's it, 16384 minus 1. Well, how much is it? So 16384 of if I erase delete this, so it's, how much was it? It's 4894, right? 4894. So if I just want to make sure it's satisfying this inequality, what is it? This inequality, to make sure whether it satisfies. So it's bigger than less than 2 times 16384. This. It's not true, right? It's way smaller. This thing is way smaller than the left-hand side. So it's not true. It's not true. So the first two sequence doesn't gives me the correct number. So how about we use 0, 1, 2 instead? So 0, 1, 2. So I get 1 over 3 over 2. So it's 2, right? 2 over 3. Yes, 3 over 3. So you can check again whether the errors are less than this number, but that's not less than this anymore. So I keep doing it. 1, 2, let's see, just cheat a little bit here. So if I go up to here, so I get 54 over 77. If I go up to one more step, then I get this. Okay. Now, so far, what I get is when I have these as my q over p, then r it means R equals to 77. So, but if I get one more sequence in here, then it means that R is 2705. Okay. So I cannot have the ratio, I mean, period, bigger than, in this case, 2 to the 7. 2 to the 7 is the half of 2 to the 14th, and it's 128. So I cannot have R bigger than half of my entire sequence, length of the sequence, because that contradicts our assumption. So this doesn't happen here. I can go only this much, that R is 77. So let's check whether this is actually less than this 2 times 2 to the n. So remember this 54 over 77 here. So if I go by 7, then it's 77, 54, and 16, 384, 11, 490 minus 77, 54. I'm going to use computer here. Let's see, let's compute. 11490, 16, 384 minus 5477. It's 0701 something. Oh, sorry, I made a mistake here. Oh, yes. So here it's 4.76 times 10 to the minus 6. And let's compute the upper bound. So 1 over 2 to the power of 15, because n is 2 to the power of 14. This is 2 to the 15 is 3.5, 10 to the minus 5. So actually it's less than. So here we have 54 minus 77 gives you approximately the error between these two numbers as something 10 to the minus 6, but 1 over 2 times 2 to the n gives much better, a little bit bigger than the error here. So it satisfies inequalities. So if you just want to satisfy the inequality, if that's your purpose, then you can go further than this sequence on the convergent. So you can go further than 7 to make the error a lot smaller than this, keep making smaller than this 10 to the minus 6 power. However, we want to find the number whose denominator represents the period. So we cannot make a period arbitrarily big. So always have upper bound. So this is as far as it can go, and this is the only place it satisfies this inequality. So therefore, what we can say about the period is that it's 77. Okay. Now, it could be the only period, it could be the largest period, but what we can do here is taking one more measurement with the circuit and find another y. And once we have y, we can do the same thing again with the new y and find another r. So if r happens to have the same 77 all the time, then you can assume that this 77 is the period. But sometimes, if this is really the period, you might get r equals to 7 sometimes. Why? Because if 77 is the period, then it means that not only entire 77, or maybe, sorry, so entire 77 number of strings or a string of numbers are periodic with the different numbers. It could have like 11 part of that, 7 of 11s. Here is 11. Oh, sorry, so 7, sorry, not why I'm saying 11. So maybe, so first 7 strings in this 77 string of letter or number are periodic, and repeating 11 times to make 77 as a periodic throughout this table. So therefore, you might get something like r equals to 7. So that means actual period is 7, right? Instead of 77, it's actually 7. So you need to take the measurement sufficiently many times so that you get the exact period of the periodic function f here. Okay, so before I think we should talk about why such period finding method is useful in a practice. So then we can talk about this continuous fraction a little bit more. Or let me tell you about another example here. So it's in the slide anyway. So by the way, the reason why I didn't use the slide for the first part is that there are many mistakes here. So I don't want to go over. For example, if I have to explain this, there are so many typos that I don't want to use this part. So, but just using the numbers as an example here. So here's another example. So same number of n, the number of input register, but let's say we took the measurement here, and we took the measurement twice. So we got the different numbers for r, and what we do is finding the period by using the continuous fraction. So we take the continuous fraction of these two numbers. So there's another typo. It's not significant, but so here we have the continuous fraction. So what we do is the same thing, that increasing the sequence in the continuous fraction until the denominator don't exceed 2 to the power of 7, which is the half of the 2 to the n. So this is how far we can go. That's when r equals to 13, and we're assuming that we took the second measurement to get this number again, and we got this number. Okay, what does it say? Okay, so we have 13 and 6 as, well, let's see. So as our candidate of R. So assuming that our Y, the number 11,000 and 13,000, this Y, satisfies our condition that the difference between Y over, was it? So Y is given by, what was it? So plus delta J here. So Yj was J times 2 to the n over R. So assuming that our Y actually is of this form, that means this is what we want. We got R equals to 13 and 6. What we should conclude is that it has both period 13 and 6. So therefore, the greatest common multiple, least common multiple of these two numbers, which is 78, must be the period. So if you take a quantum circuit and take a measurement every time, and you got 13, 6, maybe sometimes you might get 78, but that's the only number that you get, then it means that 78 is actually the period here. So that's how you get the period of a function in the oracle. So if you want to, so now we're trying to turn our attention to how we get the period, to why we get the period, why we want the period. So before we turn our attention, I want to take any questions if you have on this contingent fraction. Although I didn't explain theoretics behind the contingent fraction, but if you want to know, we can go deeper into this right now, or we can jump into the reason why we're using period finding. So, any questions? Okay, so let's talk about. So, maybe I think after we talk about why we use continuous fraction to find period, maybe it's more evident how this Shor's algorithm is useful finding or decrypting the RSA. Okay, so RSA is a type of encryption when you use distributing your key or sending a message. So let's talk about RSA. Maybe some people know about RSA, but maybe not. So I'll explain the basic idea of what RSA do. So there are two people. It's assuming that are hypothetical people, Alice and Bob. And here, Alice is a receiver, and Bob is a sender. So you have to understand the protocol, how it works. So Bob is the sender who sends the message to Alice, but it is the Alice who publishes the key. So here the key is called the public key. So first Alice publishes the key. Key is the tuple of numbers. Oh, well, let's see. I want to be consistent with the slide as far as I can. So let's see. It's a pair of two natural number, large N and E. Okay. So what is large N? Maybe I should give more space between Alice and Bob. So large N is the multiple of two prime numbers. And theoretically, it can be any prime, but practically, this prime should be a large prime. Okay, so there could be a list of large primes, and the list are almost infinitely many. So they kept lots of lists. So assumption here is that by simply knowing what n is, it's almost impossible to find out what p and q is, even though they have information that it's the multiple of two large primes. In order to find what they are, they have to just test out all the primes that they have in list, whether that actually is a factor of that number. And that testing it takes so much time, so that uh, by the time that it goes by the time that they actually could find what the factor of this large number n is, it has been too long, so that the information has been transferred, and they don't really require to keep this public key anymore. So actually you can see that the the you're using public key in Korean. So if you're trying to make a bank transactions, then you need a key. Like you have to have a USB, some data file stored in the USB storage device, so that you always have to use it whenever you log into your bank account, and it uses some RSA 128 or 256 and so on. So it uses RSA, and they're using it because in theory it takes about like 10 years if they use all the computing power in on Earth to find out what the P and Q is. So that's supposed to be safe within the year of one or two. Thinking about there could be a luck to find what P and Q is. So if anyone wants to hack your key. So anyway, so that's theory. That's a practice, and theory is just the two primes. And what is E? So E is a number that satisfies this equation. So what do I mean by this? D and E are both natural number, and E is a number that multiplied with some other number D, so that it becomes 1 when you divide by P minus Q times Q minus 1, and the remainder is 1. So let me write it this way. So DE is P minus 1, Q minus 1 times K plus 1. So mod means that it's the remainder after you divide by the number next to the mod. Okay? So Alice published this key. So it's a key. Key is just a pair of two numbers. And Bob knows it. And not only Bob, everyone knows it. Everyone knows what the public key is. So Bob, as a sender, prepares the message. So he wants to send the message in binary number or number. Let's say mu here. So how do you transform your message into number? It's easy. If you have a string of characters, you use ASCII code, whatever, so you can map each letter to a number, and then you simply put the number in a sequential order, or you can make it every number into binary digits of 8-bit number or 16-bit number, and then you just make a big chunk of your strings of zeros and ones. Okay, so for example, if you make a chunk of your message into 4 16-bit digit number, then it means 64-bit string of your 64 bits string, and it could be how many, like 0 to 2 to the 16 in principle. So you get a number, right? So, and then if your message is long, then you can have lots of numbers in sequential order, so you can send it one by one to the Alice receiver. So that's mu, the chunk of your message transformed into a number, and then encrypt to another number C by the following way. So you take the public key E, okay, and then you take the power of mu to the E, and then the remainder is C when you mod out by N. Okay, so everything is known. Mu is and N is known, E is known, and mu is what Bob prepared. He knows it, so he can convert it into some number called C here, and Bob sends C. So since C is not same as mu, nobody can know what the message is. Even they decrypt, even they translate it into another symbols, it's gonna be a illegible strings of letters. So and then send it to Alice. So what Alice do next? So after receiving Bob's message as C, so the third step is decrypt the message C by taking, so now E is the part of public key, but you have a counterpart to E, which is D. D is kept to Alice secretly. D shouldn't be published because D is the secret key. So what Alice is doing is taking D as exponent of C, and then what he gets is the original message of Bob try to send. Okay, so try, and Bob prepared and mod out by N here. So now they can transmit the message. So what's the theory behind it? We have to explain about the theory. Well, why does it works? So first of all, let's talk about Fermat theorem. It's called the Little theorem. So it says, whenever you have a number, a natural number, A, and if you take the power of p minus 1 and mod out by p, you always get 1. So as long as A is not 0, or at least it's not a multiple of p. Okay. So I'll give you an example here. So let's say we have p equals to 5 and A equals to 2. So I'm going to take exponent of 2. So 2 to the 0, 2 to the 1, 2 to the 3, 2, 3, 4. So it's 1 when I take the zeroth exponent. It's 2 and 4. And now it's 8, but that's actually by taking multiple of 2. And what you know about 8 is when you multiply by 5, it's same as 3. Okay? So the next one is 2 to the 4, but instead of taking multiple of 16, you can simply take the multiple of 3 to get 6, and which is equals to 1. Okay? So the reason why I'm telling you this is when you take the powers of number, and what you want to get is just the modulo after dividing out by number, then you don't have to keep the actual number. Simply, you can take the modulo of the previous number and then take the multiple. So I'll explain why this is important. So here, this example shows that why Fermat's little theorem holds for this small prime and number, but it holds for every number here. And think about Bob's plan. Bob is trying to take the exponent of mu. And you see, n is big number, really big number, and e is a really big number. So for example, if mu is, it's not as big number as still, but let's say let's see 2 here, but just an example. And e is, let's say, 1,000. Okay. So and let's see. And you're trying to say mod 15. Well, 15 is not a big number. I'm just assuming that it's a big number because if I really get the big number, I cannot compute. So how do you compute this 2 to the 1,000 of mod 15? You're not actually getting 2 to the 1,000 number because all we need to know is the modulo. Okay? The modulo means the remainder. So therefore, what we're doing here is taking 2, so that's 2 to the power of 1, and just twice, keep making it twice, so until you get 4, 8, and 16, and now 16 actually becomes 1 again. So from now on, you're not going to take the 16 anymore. You're starting over with 1. So you get 2, 4, 8, 16 for the next term, and then you keep doing it 1,000 times, you get the modulo. Okay. So, and also there is another way of doing this, because the 1,000 can be considered as, let's see, 112 plus 488, and this is same as 512 plus 256, and then plus 282. Hope it's right. So, and then, oh no, it's not 8. So it's, sorry, so 2, right? So, and then, so it's 2 to the power of 8, no, 9, 2 to the power of 8 plus something, right? So once you have this binary expression of your exponent, then 2 to the 1,000 can be split into this way, right? So, and then how do you compute 2 to the power of 2 to the power of 9? It's by taking repeated square 9 times. So you don't have to actually need to compute the multiple of 2 500 times, because it takes a lot of time. Instead, you can just take 9 operations by taking squares. So you just take the square of squares 9 times, and here you get the squares 8 times of squares. Squaring 9 times, and here you're taking squares 8 times, and so on. So what I'm saying here is taking exponent, or taking exponent of something, doesn't take really much time. Okay, so it's an easy computation, so that Bob can prepare its message easily, and also Alice can decrypt the message easily. Okay, so, and then what does format sensitive theorem tells you about? Okay, so it tells you about something. So what Alice is doing is, he got the message C from Bob, and he take the exponent of D. But C is actually mu to the power of E, right? So what Alice is doing is equivalent of taking mu to the power of DE. And what we know about DE is that it is modulo 1 when you multiply P minus 1, Q minus 1. So it's same thing as P minus 1, Q minus 1 times K plus 1. So you can rewrite this as mu times mu P minus 1 times, oh, sorry, so it's, okay, so Q minus 1 here. And you're taking modulo n, okay? So let's think about what is mu P minus 1, Q minus 1, modulo n. So maybe, what is this? Modulo n. So by Fermat's little theorem, what it says is, it's whatever that is, when I take natural number A, when I take the exponent of P minus 1, it's same as 1 when I multiply P. Okay, so let's put A, instead of A, let's put mu to the power of Q minus 1. Okay, and it says that if I take mu to the power of Q minus 1 times P minus 1, exactly the same as this one, then I get 1 when I multiply P. And you get the same thing by same idea, that if you put the mu to the power of P minus 1 and take the exponent of Q minus 1, you get 1 of Q. So you have the same number, And it says when you multiply P and Q, you still get 1. So the only possible way of writing this in terms of multiple of P and Q is the following. So you have P minus 1, Q minus 1 equals to, let's say, PK. So from here, let me write it here. So let me here, what it implies is that it's PK plus 1. Okay. So knowing that, it says when I divide out by Q, um, mm, the same, so it's equal here. So P and sorry, so it's maybe okay. So Q, when I divide by this part by Q, I also want 1, right? Yeah. So so it means that if I take this mu to the power of something and take minus, it means that it's divisible by Q. So it's somehow P times Q times K prime. Because we have 1 already, and if this is not the multiple of Q, you're not gonna get 1, right? So we have already remainder 1. So this pk must be a multiple of q so that we get the remainder 1. So it's the same thing here. So you have u mu p minus 1 q minus 1 equal, as a natural number, somehow p times q times some natural number k prime plus 1. Okay. So when you mod out this by pq, which is n, you always get 1 again. So let me give an example here. Let's try with an example. So P, Q are 3 and 5, and then N is 15. And let's say our Bob sent the message mu equals to 2. Okay, so let's find the public key and private key. The private key is D, which Alice keeps. So here I want to find DE equals to 1 modulo 2 times 4, which is 8, because P minus 1 times Q minus 1. So let's see, not every D and E satisfy this. So let's see, I want to find PE times E as 3. So there is a way you can pick your E or D. You can pick E or D, which is co-prime to the number 8. So 3 is co-prime to 8. So the co-prime means that it has no common divisor. So 3 and 8 doesn't have any common divisor. So if I took E, it goes to 3. And what is D? What should be D? There's only unique D satisfying DE modulo 1. So let's see. Oh, D is also 3, right? It's easy. So let's try the make encrypted message. So Bob prepares C by taking mu to the power of E, which is the public key, which is 8. And he tries to mod out by 15, but it is 8 after mod out, so it's 8. So 8 is sent to the Alice. And what does Alice do? 8 is the received message, encrypted message, and Alice is trying to decrypt by using D. So 8 to the power of 3. So you can do it by first 8 times 8, which is 64. And we're trying to mod out by 15. So 64 is mod 4 when you divide by 15. So it's 4 times 8. And it's 32. So when you mod up by 15, you get 2. So that's the original message, mu. mu, but Bob sent here. Okay. So let's talk about, so this protocol, I'm not saying that this is completely safe, because there are information that is public to the eavesdropper. Okay? So every time you try to send the message, the reason why I'm doing the encryption is that you don't want the message to be seen by any other people. Try to hack the channel between Alice and Bob. But let's see, what's the strategy for eavesdropper if he hacked the channel and saw the information that transmitted between Alice and Bob? So Alice already published the key NNE. So in fact, it not not public to everyone intentionally. It just transmitted to Bob, but it's an open channel, so anyone eavesdropper could see. So that's information that eavesdropper here Eve. So eavesdropper could see, and Bob sent the message C. So in the perspective of eavesdropper Eve, these three numbers are only available for Eve's. So, but Eve also have an information that how these numbers are made. So what Eve wants to find is what are the primes that makes n. So all what Eve wants to know is how to decrypt the message C. So Eve wants to find Alice's private key. So actually this is not the direct question that Eve wants to find. Eve wants to find what is the private key? D that Alice has. That's the main question. That's the main question. And assuming that there's no other way of finding this key, Eve have to guess it. Okay? Only way he can get this, I mean, find out what D is to guess. But he cannot, try out from one to large number, but it will take lots of times. So Eve wants to find a clever way of doing this by saying that if I could find the prime that make up the number n, then I can find what D is, because if I know that D's prime, then I know what my P minus 1 times Q minus 1 is, and I know what E is, which is public key. All I need to know is the inverse of E modulo P minus 1 and times Q minus 1. So this is inverse to E. So in multiplicative inverse to E. So again, so finding this box, the number goes into this box, is easy when you have this number, P minus 1 times Q minus 1. And E is already known, so it's a simple calculation. So easy that you can just do it instantly. So this is what we want. Eve wants to know this number. But only way he can find out what this is knowing what P and Q is. That's why Eve tried to find the primes. And as I said, since n is large number, finding such prime one by one takes lots of time. So that's why this RSA encryption is believed to be safe. But if Eve know how to find this PQ easily or comparatively faster than doing brute force checking of this prime factor, then this RSA is not safe protocol anymore. And well, the final line is that Shor's algorithm gives way faster than classical algorithm to find this P and Q. So that's why people are trying to get the quantum computer or trying to get another way of encrypting the message that is proof that is safer than this RSA. So anyway, so now, so how does Eve try to find out the prime? So here is the way he can try. So let's assume that there's a function that computes the modulo of a to the power of r with n, modulo n. So here, n a is not 0 nor 1. Okay, so let's assume we have this function and the quantum oracle UF according with this function f. Okay, so it's also another question that so this is just arithmetic definition, the definition with the arithmetic operations, and also some modulo going on, but the all assumption that Shor's algorithm can break the RSA depends on the fact that we have a quantum computer that has a large number of qubits, and also there is a way you can implement this quantum oracle with this specific function on it. Okay, so we're assuming that we have such oracle. So what does this function, what is the property of this function? So let's give it an example here. So I set this n equals to 15, and let's say, oh, I'm gonna make a different example, a equals to 3. So f of 1 is 3, f of 2, let me write it in the row. So f1, f2, f3, or maybe it's better to write in this way. So f of n here, and n here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay. So I'm going to take 3 to the power of n every time and modulo by 15. So it's 3, 9. Now it's 27, but 27 is 12 modulo 15. So I keep 12 here. And times 3, I get 36, but it's 6 modulo 15. I get, next one is 18, but 18 is 3 modulo 15. And what's next? It's 9 again, right? So I get the 3, same 3 from the beginning, right? So I get 12, 6, and 3 again, and 9, 12, 6, 3, and 6, 9, sorry, 9. Right? So it's periodic. It is periodic. So we want to find the period. What does this period say? So you can say that this period is multiple of 4 because 1, 5, and 9 are repeating, right? 9, and next one is 13. So we have period is 4. So f is a periodic function with period r, and you can imagine, do you have any guess that period 4 must satisfy? Well, in this specific example, it can be anything, but look at what p minus 1 times q minus 1 is. So here, uh, p is 5, p is 3, so it's 2, q is 5, so it's 4, so it's 8. And 4 is a divisor of 8, and it's not coincidence. So whatever you get as a period, it must divide the p minus 1 times q minus 1. So let me write it here and then try to prove it. So that is a divisor of p minus 1 and q minus 1. So why? Why does it always happening? Because let's say R is really a period. Although, so I think I should try using other symbol here. So maybe X instead of R here. So X is a variable here. Let's say R is a period. Of function f of x given by ax modulo n. Okay. Then, okay, so here is the thing. So we have a to the r equals. So I think I should wait. I made a mistake. So here, maybe I should make mistake somewhere. So 3, 9, 27, 27, 12, 36, 6, 18, 3. Right. So I get the same thing again and again. Right. So yeah, I've been okay. So let's so the what things I'm confused with. I was thinking that if I should get 1 in my list of my function, but it didn't appear. The 1 doesn't appear. So I was thinking whether I did the computation wrong. So 18, 3, 36, 6. Okay. Okay. So I shouldn't use the 3. Sorry. 3 is the prime number, which is the factor of 15. So that's why okay. So, yeah. Okay. So, uh, A shouldn't be P or Q. Okay. Here, so you can choose any A except for these 4 possible numbers. You can pick random A in practice because it's a really rare chance that your randomly picked number is either these four numbers, because you can choose any number in between 2 to n, and you pick random number, and the chance that it's a factor of a number n is really low because it's a multiple of big prime. So yeah, I'm sorry. So I shouldn't choose this three. Sorry, so I should choose, let's say, four. So instead of three, let's pick four. All right. So four. So four is simple, but anyway, I can do it here. So if you take the multiple of four and four, you get 16, but you get one again. Okay. So you get the 4, 1, 4, 1, 4, 1 going on. So what's the period in this case? So its period is 2. Okay. In this case, you get period 2. So let me do it another one. So if I have, instead of 4, let's see, 7. Got 7. So it's 49. 49 is 19. Oh, no. 15, 49, 45. So it's 4, right? So, and then if I take a multiple of 7, 28, so it's 13. And then multiple of 7 to get what? So you can consider 13 as a minus 2, actually, because you take out 15 from 13, then you get minus 2. So it's a minus 14. So minus 14 is equal to 1. So you get 1 again. So now you get the 7 back again. 7, 4, 13, 1. So in this case, you get the period of 4. Okay? So depending on A, you could get some different period, but no matter what the period is, they are always a divisor of 8. Okay, 2 or 4. Okay? Now, why is that? So let's say we have a period, then it always comes back to the when you jump r times from anywhere, you always get to the same number. So suppose that you started from a to the power of 0, you get 1 when you get the power of 0. So you jump r times, you come back to 1 again. So when you take the r exponent to any number a, you get 1 modulo n. And let's see. What you know is you have this is always 1 modulo n. Okay, and this is the largest exponent that you can get when you take that exponent to a number a so that you get 1. So this p minus 1, q minus 1 is the largest exponent satisfying this equation. So if r satisfies this, r must multiple of these number. So r must divide this integer. Okay. So so where are we? So now suppose now here is Eve's tactic. Eve uses quantum circuit or quantum Fourier transform and the oracle of function that implements this function and tries to find the period. And he got the period using continuous fraction, all the things that we have discussed before. Got the period and lots of period. And what he do with this period is making up the candidate of P and Q, because he knows, Eve knows that whatever the value of he found as a period is a divisor of P minus 1 and Q minus 1. So Eve finds the candidate of divisors of p minus 1 times q minus 1. Okay, he doesn't know what p and q is, but so what he only knows is a divisor that is some unknown number, and he tries to make up the possible way of combination of getting this p minus 1 times q minus 1. Then he finds all possible combination of divisor so to make a number to make p minus 1 q minus 1. Okay, so for example, suppose that Eve's got the candidate of the period R equals to 2, 4, 49, and 81, 9, and let's say 7. Okay, he did lots of experiment, and then he got these numbers. Okay, no more. So I don't mean that he only did six measurement. I'm saying that he did a lot of measurement, like 1,000 or 2,000, and every time he run the circuit, the period he could get is only these six numbers. So it means that the p minus 1, q minus 1 that the Eve tries to find divides 4, 49, and 81. And not only that, but since he couldn't find a bigger multiple of these numbers, for example, he couldn't find 8. So that means this p minus 1, q minus 1 couldn't contain 2 to the power of 3. There are only 2 multiple of 2 divisors in this p minus 1, q minus 1. So Eve could guess that this number is p minus 1, q minus 1 is this. Okay? So now, what's Eve's strategy? He tries to find what p and q is. So he tries to deduce what p and q could be. So for example, if so this is just simply multiple of 2 integers. For example, I can split this into 4 times 49 times 81, or I could split it into 2 times 49 times 81, and so on. There are lots of, but finite many of a combination of splitting into multiple of 2 integers, right? So let's say in this case, so he has to guess all possible combination of the multiple. So for example, if I assume that 4 is p minus 1, that means that p is 5, and in this case p is 3. And now I have to guess what the q is for in this case. Let's say 49 times 81. Let me go back to the Python here. Compute 49 times 81. Uh, 3969. Yes. So if this was q minus 1, q must be 3970, right? So now we can check whether this is prime or not. It's not a prime. Okay, so he can rule out this possibility. Okay, so then he goes to next one. So if this is true, if this is possible way of p minus 1, q minus 1, then q must be twice of this, right? So it's 8 plus 1. So 8, 3, 9, 7. So it's 7, 9, 39. This prime looks like it's prime, but not sure. But anyway, so if it's the prime, I think it's prime, then he have still a candidate of 2 primes that gives the number n. Since he know what number n is, it's simple to check whether your number 3 times 7, 9, 39 is actually the same number you get. Actually, the same number that published to everyone. Okay? So he can keep doing it. If it's not the same, then he can go on to another combination of number of factors and then move on. So, by the way, and we have to assume that the the period that we get every time by measuring is falling to the category of y equals to some integer multiple of 2n over r with the error less than 1 over 2. It's only when we assume that. But when you take the measurement, there's no guarantee that your measurement outcome is in that format. So therefore, there's also possibility that you have to rule out some of the result as a period is not really a period. Okay, as I said, only 40 above than 40% chance you get the correct form of y that you can deduce the correct period, but it means that there is still at most 40% chance that you get the wrong number or wrong format of y, so that you don't get the correct information about the period. So even though the Eve couldn't make up P and Q that consists the N, it is public, he also has to think about other possible way of combining, make a combination of numbers so that you have, sometimes you have to rule out, possibly rule out some numbers, assuming that this is not correct and so on. And do the same computation again with these choices of numbers. But still, there are finally many choices, and still that's way faster than checking all the numbers for finding the factors of large number n. So it's more effective than this, more effective than brute force finding of the factor, prime factor. So that's basically what's going on. Oh, we are already over time. So if you have any question, let me know. And also, well, if you already have a simulator, then it's actually one thing that you can implement on your simulator, because now you have, so you have to, in some sense, in order to simulate this Shor's algorithm to find the period, the one thing that you have to fake is the quantum oracle of this function. So what I mean by fake is that you need to know all the possible values of functions already to implement the oracle. But if you have all the information of this function, then you don't need to find the period because it's already there. You can just check from beginning to see what the period is. And also, the Eve knows the list of all the functions and the value of functions, then he doesn't need the quantum circuit. He can just find the period right away. But that's impossible. But if you want to simulate, you have to fake this so that it have all the information, but assuming that this is somehow magically appeared without knowing the function. So yeah, so you can show how the Shor's algorithm works on your simulator in that case. So that's basically Shor's algorithm. We didn't go through lots of details in the continued fraction, but there are lots of sources that you can find out more on the continuous fraction. Next time, I think we can move on to other algorithm, Grover's algorithm, but I want you to think about, I forgot to post my video clip last time, but I will do today. So after watching or looking at the lecture note again, and if you have any questions about the Shor's algorithm, how it works, and we can spend more time next lecture to answer the questions and think about more examples. Otherwise, we can move on to the Grover's algorithm, and then after we've done the Grover's algorithm, we can move on to the quantum error correction part of the quantum computing. Okay, see you on Wednesday.